just to make sure we're all on the same page here, when we're talking about x bar, we're talking about the sample mean. When we're talking about s squared, we're talking about the sample variance. Anytime we're talking about a sample, we use English letters. Mu is the population mean, and this is the population variance. Again, for populations, we use Greek. For samples, English. For population, Greek. Just a real quick review. When we're trying to estimate the population proportion, we use a z. When we're trying to estimate a population mean from a sample, and the standard deviation of the population is known, we use a z again. But to estimate a population mean from a sample where the standard deviation of the population is not known, which is actually more typical, we have to use a t as our critical value. For variance, okay, from a sample, to estimate the variance of the population from a sample, we have this formula, n minus 1, where n is the number in the sample, times the standard deviation of the sample squared over chi squared right. Okay, that's our critical value for variance, just like z's and t's for proportion and mean. The actual actual variance of the population is somewhere between n minus 1 times the sample standard deviation squared over chi squared right, and n minus 1 times the sample standard deviation squared over chi squared left. Top of the two are the same. We've got to find a right chi squared and a left chi squared to use in that formula. So to use a problem that we've looked at before, where we have 106 body temperatures, the average of the sample is 98.2 and the standard deviation of the sample is 0.62. What we want is to estimate at a 95% confidence level the standard deviation of the population. Again, we're estimating a population from a sample that we have. The chi squared is a different creature than the z or the t. It's not normally distributed. Starts at 0 and goes up rapidly and then goes down slowly so that it's curved like this. Now, to get your critical values, your chi-squareds, from the table where n equals 106, you're going to use the degrees of freedom of n minus 1. The degrees of freedom is always n minus 1, both for the chi-squared and for the t distribution. So in this case, it's going to be 105. You don't have 105 in your table. The table's in the back of the book or on this handy-dandy little chart that is in the book. We use the closest one to that, which would be 100. And we look to the area to the right of the critical value. If we're at a 95% confidence level, we want 95% in the middle here. So there's 0.025 out here, 0.025 out there. For chi-squared left, table asks for the area to the right, it's going to be 0.975, 0.95 plus 0.025. For chi-squared right, it's the area to the right of that is going to be 0.025. And if we look up using 100 in the chart, for those two, we're going to get a chi-squared left of 74.222 and a chi-squared right of 129.561. And then we have everything we need to put into our formula for the standard deviation or the variance. Again, here's our formula for the variance. N is 106 minus 1 times the standard deviation of the sample, 0.62, over chi-squared right, which is 129.561. This variance of the population is going to be somewhere between that And 106 minus 1 times 0.62 squared. Numerators are the same. Chi-squared left from the table is 74.222. And if we do those calculations, we get that the variance is somewhere between 0.311528 and 0.543801. And as we looked at before, percentages, the means, and the variance, when we take all possible samples of a certain size, we can use those as good estimates of the population. One final thing to do. We ask for the standard deviation of the population. This gives me the variance. So get the standard deviation. I take the square root of everything. And the standard deviation of the population, I am 95% sure, is located somewhere between 0.56 and 0.74. Again, from a sample of 106 with a mean of 98.2, which we really never used, but a standard deviation of 0.62, from that sample, we estimated that the standard deviation of the population is somewhere between 0.56 and 0.74.